Reflection in Java is a powerful feature that allows programs to inspect and manipulate the runtime behavior of applications. It is part of the java.lang.reflect package and provides methods to analyze or modify the behavior of classes, methods, fields, and constructors, even if they are private or protected. Key features of reflection include the ability to analyze class properties, invoke methods, and access private fields. It also supports dynamic class loading and runtime type identification. Let's see some of them. 1. Runtime inspection. It enables the examination of a class's structure, including its fields, methods, constructors, and annotations, at runtime. 2. Dynamic access. It allows instantiating objects, accessing fields, and invoking methods dynamically at runtime without prior knowledge of their details during compile time. 3. Access control override. It can access private fields, methods, and constructors by overriding Java's access control checks. 4. Works with annotations. It allows introspection of annotations on classes, methods, and fields. Reflection is widely used in frameworks and libraries for tasks like dependency injection, object serialization, and testing. It enables dynamic proxy creation and facilitates runtime code analysis. Some of them are: 1. Framework development. It widely used in frameworks like Spring, Hibernate, and Junit to dynamically instantiate classes and invoke methods. 2. Dynamic class loading. It helps load classes at runtime without prior compilation, enabling dynamic behavior. 3. Testing. It facilitates testing of private methods and fields without modifying class visibility. 4. Runtime configuration. It used for dynamic configuration of applications based on user inputs or configurations. 5. Debugging and profiling. It enables runtime analysis and profiling tools to examine program execution details. 6. Custom class loaders. It works with custom class loaders to define and load classes dynamically. The advantages of reflection include increased flexibility and the ability to create more generic and reusable code. It allows developers to write code that can adapt to different situations dynamically. However, reflection has its disadvantages. It can lead to performance overhead due to dynamic type resolution and can make code harder to understand and maintain. It also poses security risks. Reflection should be used judiciously, primarily in scenarios where dynamic behavior is essential. It is best suited for framework development, testing, and situations requiring runtime adaptability. If you found this video helpful, please subscribe to our channel for more insightful content on Java and other programming topics. Your support helps us create more valuable resources. Thank you for watching our video. We appreciate your time and hope you gained a better understanding of reflection in Java. Stay tuned for more educational content. Welcome to our channel. Stay tuned for more informative content on Java exception handling. Don't forget to subscribe for updates and new tutorials. Exception handling in Java is a mechanism that allows a program to deal with unexpected events or errors that occur during execution. It provides a structured way to manage errors and maintain the normal flow of the application. Here are the key concepts involved. First, exceptions. Exceptions are events that disrupt the normal flow of a program. They can be caused by various issues, such as invalid user input. Second, types of exception. There are two types of exceptions. 1. Checked exceptions are exceptions that are checked at compile time. The programmer must handle them using try-catch blocks, or declare them in the method signature using the throws keyword. Examples include IO exception and SQL exception, while unchecked exceptions are checked at runtime and include errors that are typically due to programming mistakes, such as null pointer exception, array index out of bounds exception, and arithmetic exception. They are not required to be handled explicitly. The key difference between checked and unchecked exceptions is that checked exceptions must be declared or handled. In Java, a custom exception is a user-defined exception class that extends the exception class, or a subclass of it, to represent specific error conditions that are not covered by the standard Java exceptions. Custom exceptions allow developers to create meaningful and specific error handling in their applications, making it easier to manage and understand error states. Some of key points are specific error handling. Custom exceptions provide a way to handle specific error conditions relevant to your app. In Java, the throw keyword is used to explicitly throw an exception from a method or a block of code. When you use throw, you must provide an instance of throwable, which includes exceptions and errors. This is typically done to indicate that an exceptional condition has occurred. Some of the key points are 1. You can throw both checked and unchecked exceptions using throw. 2. When you throw a checked exception, the method must either handle it with a try-catch block or declare it using the throws keyword in the method signature. 3. The throw keyword is different from the throws keyword, which is used in method signatures to indicate that a method can throw certain exceptions. In Java, the throws keyword is used in a method declaration to specify that the method can throw one or more exceptions. It indicates to the caller of the method that they need to handle those exceptions, either with a try-catch block or by declaring the exception in their own method signature using throws. Some of the important key points are 1. The throws keyword is typically used with checked exceptions, those that are subclasses of exception, but not of runtime exception. Unchecked exceptions, like null pointer exception, do not require a method to declare them with throws. 2. You can declare multiple exceptions in a method signature by separating them with commas. 3. Using throws allows for the propagation of exceptions up the call. The finally block in Java is a special block used in exception handling that follows a try block and, optionally, one or more catch blocks. It contains code that is guaranteed to execute regardless of whether an exception was thrown or caught. This makes it an ideal place to perform cleanup operations, such as closing files or releasing resources. Some of the key points of finally block are 1. The finally block is executed regardless of how the try block exits, whether normally, through a return statement, or due to an exception. 2. Cleanup operations. It's commonly used for resource management, ensuring that resources are freed up, such as closing files, sockets, or database connections. 3. Optional. A finally block can exist. In conclusion, understanding exception handling in Java is crucial for writing robust code. Don't forget to subscribe for more Java tutorials and stay updated. Welcome to our channel. Today we will delve into the Java memory model. Stay tuned for valuable insights. Understanding the Java memory model is crucial for Java developers. It helps in writing efficient and error-free code, ensuring optimal performance of applications. This knowledge is indispensable. The Java memory model defines how threads interact through memory. It specifies rules for reading and writing variables, ensuring consistency and predictability in multi-threaded environments. Let's illustrate how the Java memory model works. Imagine multiple threads accessing shared data. The model ensures that changes by one thread are visible to others, maintaining data integrity. Now let us understand the structure of the Java memory model. In Java, memory is divided into the main memory and working memory, or thread local memory. First, main memory. This is the shared memory where variables are stored, such as heap and static fields. All threads have access to the main memory. Second, working memory, thread local. Each thread has its own working memory that stores copies of variables from the main memory. When a thread performs an operation on a variable, it typically uses this local copy rather than accessing the main memory directly. Now we will understand happens before relationship of memory model. The JMM establishes a happens before relationship, which is a set of rules that defines when writes to a variable by one thread are visible to other threads. Some key rules include 1. Program order. Rule: in a single thread, actions happen in the order written in the program. 2. Monitor lock. Rule: an unlock on a monitor, synchronized block, happens before any subsequent lock on that monitor. 3. Volatile variable rule: a write to a volatile variable happens before every subsequent read of that variable. 4. Thread. Start rule: a call to thread, start, happens before any action in the started thread. Fifth rule is thread. Join rule: all actions in a thread happen before any thread successfully returns from a thread, join, on that thread. Overall, these rules help to ensure that certain operations are visible to other threads and maintain data consistency across threads. Now we will understand third important concept, volatile variables. In Java, the volatile keyword is used to indicate that a variable's value will be modified by different threads, and it ensures visibility. When a variable is declared volatile, any read or write to that variable will go directly to main memory, and updates to it are immediately visible to other threads. Now explore the concept of synchronization and locks. To achieve both visibility and atomicity, the JMM provides synchronization mechanisms. 1. Synchronized blocks and methods. Only one thread can execute a synchronized block or method at any given time for a particular object. This ensures mutual exclusion. 2. Intrinsic locks, monitors. Each object in Java has an intrinsic lock, monitor. When a thread enters a synchronized block, it acquires this lock. Exiting the block releases the lock. Synchronized blocks ensure that all changes to shared data are visible to other threads and provide atomicity, which is essential in concurrent programming. Some of issues addressed by the Java memory model are: it helps solve key concurrency issues. 2. Visibility ensures that changes in one thread are visible to others. 3. Ordering helps prevent undesired reordering of operations. 4. Atomicity guarantees atomicity through synchronized blocks, locks, and atomic variables. By defining these rules, the JMM aims to prevent the most common concurrency problems, such as race conditions, multiple threads accessing shared data simultaneously in an unsynchronized manner. 2. Out-of-order execution. Modern processors may reorder instructions for optimization, leading to unexpected results without the JMM's constraints. 3. Cache coherency. Threads may work on cached copies, causing data inconsistency. Don't forget to subscribe to our channel for more informative content. Join our community and stay updated with the latest in Java development. Thanks for watching. Welcome to our channel, where we provide high-quality educational content on complex programming topics. By subscribing, you gain access to comprehensible, concise, and efficient explanations on various programming topics. Technical knowledge and programming skills, making you a better Java developer. Today we will learn about lambda expression and its features. A lambda expression is a concise way to represent an anonymous function in programming. It allows you to define a function without needing to formally declare it with a name. Lambda expressions are particularly useful for short, single-use functions, especially in functional programming and when working with collections. In many programming languages, a lambda expression typically has structure like: first, input parameters. These are the variables the function takes. Second, arrow, often represented by or, indicating that what follows is the function's body. Third, body. This is the expression that defines what the function does. Some of the usage of lambda expression are: first, higher-order functions. They can be passed as arguments to functions. Second, event handling, often used in GUI applications. Third, stream processing, used in languages like Java and Python for processing collections of data. While lambda expressions offer several benefits, they also come with some drawbacks. First, readability. Lambda expressions can make code harder to read, especially for complex functions. Developers unfamiliar with the syntax may find it challenging to understand. Second, debugging difficulty. Debugging lambda expressions can be tricky. Since they are often anonymous, stack traces may not provide meaningful information about where an error occurred. Third, limited functionality. They are typically meant for simple operations. If the logic becomes complex, using a named function is often clearer and more maintainable. Fourth, scope issues. In some languages, lambdas can capture variables from their surrounding context, closures, which can lead to unintended side effects or behavior if not carefully managed. Fifth, performance. In certain scenarios, using lambdas can introduce overhead, especially in languages that do not optimize them well. This is usually not significant, but can matter in performance-critical applications. Sixth, language support. Not all programming languages support lambda expressions, or their implementation may vary, which can lead to inconsistencies across codebases. Overall, while lambda expressions are a powerful feature, they should be used judiciously, balancing their advantages against these potential drawbacks. Join our community by subscribing to the channel and stay updated with the latest programming tutorials. Liking the video helps boost its reach, allowing more viewers to benefit from this valuable learning resource. Thank you for watching. We appreciate your support and look forward to providing more educational content. Java is a versatile programming language, and today we'll explore some fundamental concepts. These include maps, tree map, linked hash map, the super keyword, method chaining, inner classes, and static nested classes. A map in Java is a collection that maps keys to values. It cannot contain duplicate keys, and each key can map to at most one value. Maps are essential for efficient data retrieval. Tree map and linked hash map are two important implementations of the map interface. Tree map sorts entries by keys, while linked hash map maintains insertion order. Both have unique advantages for different use cases. The super keyword in Java is used to refer to the immediate parent class object. It is often used to access parent class methods and constructors, ensuring proper inheritance and method overriding. Method chaining is a technique where multiple methods are called on the same object sequentially. It enhances code readability and reduces the need for temporary variables, making the code more concise. Inner classes in Java are defined within another class. They have access to the members of the outer class, even if they are private. This allows for more modular and organized code. Static nested classes are a type of inner class that is declared static. They do not have access to the instance variables of the outer class, making them useful for grouping related classes. Thanks for watching the video. Please subscribe to the channel for more informative content on Java programming and other computer science topics. Your support helps us create more valuable content. Thank you for tuning in. Don't forget to subscribe to our channel for more insightful content on Java programming and other tech topics. Java is a versatile programming language used for building various applications. It is known for its portability, robustness, and ease of use. Today we will learn some of key features of Java, like string, string builder, string buffer, and string pool. Let us first start with string. In Java, a string is a sequence of characters used to represent text. Strings are a fundamental part of Java programming, and understanding their properties, behavior, and how they are managed in memory is crucial for effective coding. Strings in Java are immutable, meaning once a string object is created, its value cannot be changed. If you modify a string, a new string object is created instead. Some of common use cases of string are like: first, text manipulation. Strings are used extensively in applications for text processing, user inputs, and more. Second, data representation. Strings can represent various data formats, for example, JSON and XML. Third, communication. Strings are used for building messages in networking applications. Some of performance considerations needs to be taken care. For example, first, concatenation. Using plus for concatenation can lead to performance issues in loops due to the creation of multiple immutable objects. Instead, use string builder for better performance. Second, memory usage. Be mindful of memory consumption when dealing with large strings or numerous string operations. Now we will try to understand String Builder. String Builder is a mutable sequence of characters in Java designed for efficiently modifying strings. Unlike string, which is immutable, String Builder allows for dynamic changes without creating new objects each time. This makes it particularly useful in scenarios where performance and memory efficiency are critical. Some of the key characteristics are: first, mutability. Strings created with String Builder can be modified without creating new instances. This is particularly beneficial for frequent string operations. Second, performance. String Builder is generally faster than string for concatenation and other modifications, especially in loops or when dealing with large strings. Third, non-synchronized. String Builder is not synchronized, which means it is not thread safe. If multiple threads are accessing a String Builder instance, it may lead to unexpected results. For thread-safe operations, consider using string buffer. Some of performance consideration that needs to be followed are: first, when to use. Use String Builder when you need to perform many modifications to a string, such as in loops or large-scale string manipulations. Second, capacity management. If you know the expected size of the string, you can initialize the String Builder with a specific capacity to minimize resizing operations, which can improve performance. Now we will learn about string buffer. String buffer is a mutable sequence of characters in Java, similar to String Builder, but with one key distinction: string buffer is synchronized, making it thread safe. This means it can be safely used in multi-threaded environments where multiple threads may attempt to modify the same string concurrently. Some of key characteristics are: mutability. Like String Builder, String Buffer allows modifications to the string without creating new instances, which can improve performance for certain operations. Second, thread safety. String Buffer is synchronized, meaning its methods are designed to be safe to use by multiple threads at the same time. This ensures that only one thread can access a method at any time, preventing data corruption. Third, performance. Because of its synchronization, String Buffer is generally slower than String Builder in single-threaded applications. However, we need to consider some of performance major. First, when to use. Use String Buffer when you need a mutable string and are working in a multi-threaded environment where thread safety is a concern. Second, synchronized methods. While String Buffer is thread safe, the synchronization comes at a performance cost. If you don't require thread safety, prefer using String Builder for better performance. Java strings are a powerful and versatile part of the language. Understanding their properties, methods, and the differences between string, String Builder, and String Buffer can help you write more efficient and effective Java code. Now we will learn more about String Pool. The Java String Pool, also known as the String Intern Pool, is a special memory area within the Java heap that stores string literals. It is a part of the Java memory management system and plays a crucial role in optimizing memory usage and improving performance when dealing with string objects. Some features of String Pool are: first, memory efficiency. The String Pool allows Java to store only one copy of each distinct string literal, thereby conserving memory. If multiple string literals have the same content, they will reference the same object in the pool instead of creating separate instances. Second, performance improvement. By reusing string literals, Java can reduce the overhead associated with creating and managing multiple string objects, leading to faster performance in string operations. Some of precaution we should do while using String Pool. First, garbage collection. Strings in the String Pool are not eligible for garbage collection as long as they are referenced. However, they can be removed if the class loader that loaded them is garbage collected. Second, impact on performance. While the String Pool can save memory and improve performance for string literals, excessive use of dynamic string creation, using new string, can lead to increased memory usage since these strings are stored in the heap and not in the pool. Thank you for watching. Make sure to subscribe to our channel for more tutorials and updates on Java programming and other tech topics.